Black holes feel like the ultimate cosmic prison, objects so powerful and extreme that nothing, not even light itself, should ever be able to escape their pull. As gas, dust, and even whole stars spiral inward, the black hole's gravity crushes them into a violent glowing disk, making the region around it one of the brightest sights in space. At the center lies the event horizon, a one-way boundary in spacetime where every possible path points inward, and crossing it means there is no route back out. Most black holes are born when very massive stars run out of fuel, collapse under their own gravity, and leave behind a compact object so dense that spacetime folds inward. That sounds final, but quantum physics tells us that empty space is never truly empty and is always buzzing with tiny temporary fluctuations of energy. Near the edge of a black hole, those fluctuations can appear as pairs of particles that flash into existence for a tiny fraction of a second. Normally, those pairs instantly meet again and cancel out, but near an event horizon, gravity can pull them apart before that happens. One particle can fall into the black hole while the other escapes outward, carrying away a minute amount of energy into the universe. That faint escape of energy is what physicists call Hawking radiation, named after Stephen Hawking, who helped reveal this astonishing possibility. And if energy is leaking away, even incredibly slowly, the black hole cannot stay exactly the same and must gradually lose some of its mass. Over unimaginable spans of time, that means the black hole would not remain eternal, but would slowly shrink, bit by bit, as radiation escapes. This idea is so famous because it brings together two huge pillars of modern physics: quantum mechanics and Einstein's theory of gravity. Those two theories work brilliantly in their own domains, but black holes force them into the same place, where their differences become impossible to ignore. To a distant observer, the black hole can seem almost silent and dark, yet still give off a whisper of thermal radiation from near the horizon. When Hawking worked this out in the 1970s, it changed how physicists thought about black holes because it suggested they were not perfectly black after all. The result was revolutionary, showing that gravity, particles, and the quantum vacuum could combine to create an effect no one had fully expected. The smaller a black hole is, the hotter it should become, which means tiny black holes would evaporate much more quickly than giant ones. Supermassive black holes, like the ones sitting in galactic centers, would evaporate so slowly that the process would be almost impossible to notice. Their lifetimes are so vast that they stretch far, far beyond the current age of the universe and into a future almost impossible to imagine. In that remote future, after stars die and galaxies grow dark, black holes may remain among the last major objects still shaping the cosmos. But even then, according to Hawking's idea, they would keep releasing energy into the emptiness around them, however slowly that process unfolds. As the black hole loses mass and becomes smaller, its temperature rises, causing the evaporation rate to increase more and more. So the end is not just a slow fade forever, but a process that may accelerate dramatically once the black hole becomes extremely tiny. Some models suggest the final stage could end in a brief, intense burst of high-energy radiation as the last remaining mass disappears. After that moment, the black hole may be gone completely, leaving only radiation spreading through space where the object once existed. But this leads directly to one of the deepest mysteries in theoretical physics, a problem known as the black hole information paradox. If the black hole eventually evaporates away, what happens to all the information carried by everything that ever fell inside it? According to the rules of quantum theory, information should not simply vanish, even if the object containing it is destroyed. That is why black holes are not just exotic cosmic objects, but also laboratories for testing the deepest laws that govern reality. Some physicists think information may be encoded in subtle ways near the event horizon, even if we do not yet fully understand how. Others believe the answer will only come from a deeper theory of quantum gravity, one that unites spacetime and quantum rules completely. In the present-day universe, most known black holes are still gaining matter from their surroundings faster than Hawking radiation can remove it. So black hole evaporation is almost certainly too weak to observe directly for the giant black holes we see in space today. If Hawking radiation is real, then even the darkest and most powerful objects in the universe are temporary, not permanent fixtures of existence. And that gives black holes a surprising ending,